Chapter 20, we return to thinking about thermodynamics again. So a little review sheet again on the 5 things that are important to think about with regards to Chapter 20. So because Chapter 20 kind of builds on thermodynamics topics we've talked about before, we need to review some of our earlier thermodynamics topics, which especially include topics of enthalpy. So we've introduced entropy before. We're going to explore it in a lot more detail in Chapter 20. So we have another section exclusively dedicated to entropy, and we'll get to some specific sample problems that address that. And then we also talk about Gibbs free energy. And Gibbs free energy, again, in this equation here, shows us that the spontaneity of a process, that is whether a reaction occurs, has components of both enthalpy and entropy. And as we can see here, entropy has a temperature component. So we'll work through several problems that actually allow us to think about that. And then specifically with regards to spontaneity, we'll discuss free energy, and we'll talk about kind of the different combinations of this system of entropy and enthalpy that allows us to think about whether or not a reaction will be always spontaneous, never spontaneous, or have a temperature dependence, and that is whether high or low temperatures will favor it. So we'll talk about the aspects of those 4 scenarios in a logical way, so it's not something you try to memorize. And at the very end, we kind of put all of this together and start thinking about the relationship between thermodynamics and energetics and equilibrium. And as we'll see as we kind of wrap up this chapter, an important equation allows us to relate the spontaneity or the thermodynamic driving force of a process through Gibbs free energy to the equilibrium constant. And so we have this equation that we'll use when we're at standard state. And then again, if you're not at standard state, that's what that little symbol means. When you're not at standard state, that is your Q is not equal to 1. This is going to allow you to explore different delta G values. So we'll have a whole bunch of problems then that we'll think about with regards to that. Okay, so starting this chapter, we're going to start out again, just thinking about entropy. We're going to think about it very qualitatively to start with. And basically, when we think about entropy, you want to think about more molecules moving more. And that kind of a way to think about things is going to help us predict whether entropy is higher, for example, between one substance or another, or if we're looking at a chemical reaction, which is one of your homework problems, actually trying to predict whether entropy is going to be favorable or unfavorable for that process. Remembering that favorable entropy is going to be a positive value. Okay, so for this problem, we just have to look at these 2 kind of pairs of molecules or system and ask the question, who has higher entropy? So if we look at the first one, we say 1 mole of SO2 gas or 1 mole of SO3 gas. Again, we're talking about gaseous substances, so we're not looking at a phase change. What we're really looking at, and anytime you have these problems where you're asking to compare things, ask what's different. So what's different is we have a molecule that has 3 atoms in it and a molecule that has 4 atoms in it. So if we think about the concept more molecules moving more, well, we have the same number of molecules, but there are more atoms within this molecule. So 1 mole of SO3 gas is going to have a larger entropy because there's more atoms there. So the larger the molecule is, the larger the number of atoms, the greater the number of atoms that we have, that's always going to create a situation where we have more entropy. All right, second problem here, 1 mole of CO2 solid or 1 mole of CO2 gas. And one thing that we talked about in class, we talked about the fact that it says assume constant temperature. And you might look at this problem here and say, well, wait a minute, how can we have temperature be constant and have solid carbon dioxide or gaseous carbon dioxide without looking at different temperatures? Remember back from our phase change diagrams that we had all the way at the beginning of Gen Chem 2, and we showed that by changing the pressure, you could have the same temperature result in either solid carbon dioxide at high pressure or gaseous carbon dioxide at low pressure. So again, just reviewing a little bit there is temperatures where you could have either solid or gaseous carbon dioxide depending on the temperature. But if we apply our more molecules moving more concept, molecules that are gas are going to move more than molecules that are liquid, or in this case, solid. So 1 mole of CO2 gas is going to have more energy. So when we think about, more entropy. So when we think about phase changes. Phase changes have an entropy component to them. All right, part C, 3 moles of O2 gas or 2 moles of O3 gas. Now in this case, it's actually a little bit of an apples to oranges comparison because there's two things that are changing. We are changing the molecule that we have, so it's O2 versus O3. And like we had in part A, if it was 1 mole of O2 and 1 mole of O3, the O3 would win out in terms of having greater entropy. But in this case, we have 3 moles of O2 and only 2 moles of O3 gas. So in that case, if we apply more molecules moving more, we have more molecules of gas when we have 3 moles of O2, such that the small difference in entropy that we'd have by having a third atom there is minimal compared to the actual change in the number of moles of gas. So in this case, 3 moles of O2 is going to have greater entropy. D says 1 mole of KBr solid or 1 mole of KBr aqueous. So again, if we apply more molecules moving more and we think about what it really means to go from a solid to aqueous, this isn't truly a phase change, but it is a situation that creates more disorder in the system by breaking apart these ions. So in this case, 1 mole of KBr is going to have a greater amount of entropy because we've allowed those molecules, and not really molecules, they're ions in this situation, but we've allowed them to move more. They're not specifically ordered in our crystal lattice of our ionic solid. Okay, and as our starting problem told us, every one of these problems is at the same temperature except for E, which talks about a single substance at 2 different temperatures, 2 degrees C or 23 degrees C. Again, if we apply our more molecules moving more, if we want to get molecules to move more, we increase the temperature. So seawater at 23 degrees is going to have the greater entropy. So seawater at 23 degrees C. And lastly, 1 mole of CF4 gas or 1 mole of CCl4 gas. And again, this one looks a little bit different. We technically have the same number of atoms between these two molecules, and we have the same quantity of these gases. So what's really different is the fact that chlorine is different from fluorine. Chlorine being a bigger atom makes this a larger molecule. So you can kind of think about this in a way of saying that there is not truly more molecules, but there are more of these molecules in the sense that they're larger. So 1 mole of CCl4 is going to have a greater entropy. So the greater the molecular weight, the greater the size, that's going to contribute to greater entropy. So qualitative aspects of entropy, and our next few problems will work through quantitative aspects of entropy.